Okay, we're back. Here's the second video on finding solutions to definite integrals. I have 4 more examples to go through. Just a reminder, the fundamental theorem of calculus tells us that we can evaluate the indefinite integral first, forget about the c, take that function, and evaluate it at the upper boundary, subtract the same value at the lower boundary, and then that will give us a single number as our solution to the definite integral. Here's our integral properties and integral identities that we will need in order to do step 1 of this problem. Here's a sample problem, and for sample problem number 3, I forgot to mention something kind of important, which is that t is in radians. Otherwise, you don't know whether this is 2 pi radians for this boundary here, or whether it's 2 pi degrees. Let me fold this in half just to make the paper a little easier to manage. All right, here we go. All right, so we got 12 cosine t, in definite integral of 12 cosine t from 0 to 2 pi. Step 1 is to evaluate the indefinite integral, and I'm going to use a slightly different notation than I did in the last video. So if we start with this, we can treat the definite integral symbol the same way we treat the indefinite integral symbol. So if you don't want to do this as 2 seemingly different steps, and rather just do it as one kind of longer step, you're welcome to use this notation. Either way, the laws of integration, the properties and identities of integration apply. 12 comes out. Integral of cosine, according to our list of identities, that is positive sign. And once we've gotten rid of the integral symbol and the dt, then we can just switch to that vertical line notation. Got no idea what the heck you actually call it, but you switch to this notation now that the integration symbol is gone. Then we evaluate this function at 2 pi, and then we evaluate it again at 0. So we get, and if you want to think of this as step 2, then it becomes 12 times the sine of 2 pi minus 12 times the sine of 0. And remember, we said that t is in radians, so sine of 2 pi radians, that's 0, so that's going to be 12 times 0 minus, all right, sine of 0 radians is also 0. Sine of 0 anything is 0. Oops. 12 times 0, 0, 12 times 0, 0, so we get 0 minus 0, and that means our answer is 0. Now, this might be a little weird, or a little difficult to interpret, once you remember that the definite integral is actually the area under the curve. So if this is 12 right here, and then this is 0, and this is 2 pi radians, this is a graph of 12 cosine of t dt. If this is the t-axis, and this is the y-axis, or the z-axis, or whatever the heck you want to call it, then you'll get something like this. And it looks like the area here is not 0. But if you remember all the way back to the lesson, the day 1, lesson 1 rules of integration, there are positive areas and there are negative areas. The positive areas, if we are integrating from left to right, which we almost always will be, then the areas above the curve, those are positive. So the areas that I'm shading here with this pencil, that's a positive area. And then areas below the curve, but below the x-axis, those are negative. So this orange area I've shaded, that's negative. And so what this integral, definite integral coming out to 0 means is that the gray areas are equal in magnitude, but opposite in sign from the orange areas. Gray areas are positive whatever, orange area is negative whatever, and when you take the two and subtract them, you get 0. Okay, let's look at a somewhat easier to interpret situation. We have this much. Let me just recopy it real quickly. Our variable here is b rather than x. It's all the same. Sorry, the negative sign and the fraction bar ran into each other there. But we have two functions subtracted from each other. That means we can break the integral up into two separate integrals and then tackle each identity separately. Okay? We can factor the 14 out of this one and the 8 out of this one. So we get 14 integral from 1 to 2 e to the b db minus 8 times the integral from 1 to 2 of 1 over b db. Okay. Bust out your integral identities. You got integral of e to the whatever d whatever is just e to the whatever. So we got 14 e to the b here. And then integral of 1 over x or 1 over b dx or db is natural log of the absolute value of b in this case. And we can forget about the plus c, but instead of the plus c, we put this vertical line in with the boundary values. Okay, now we first take this function. Wherever we see a b, we put in a 2. And then we take the function again, and wherever we see a b, we put in a 1, and then we take the difference between those two things. So we got 14 e to the 2 minus 8 times the natural log of the absolute value of 2 minus 14 e to the first minus 8 times the natural log of the absolute value of 1. Natural log of 1, that's an easy function to evaluate. That all comes out to 0. E to the first is just 1. This stuff you can't clean up at all, so you get 14e squared minus 8 times the natural log of the absolute value of 2 minus 14e. Alright, if you were in a math class, this would be a perfectly acceptable answer. But in a science class, you want to actually evaluate the function. So that means find your calculator amongst all these things. Give me a second. No, not that, not that, no, not that, no, not that. What's this? Mendoza sent me an email. Here we go. Alright, what do you know? I even have this already on my calculator. It's like I did this before. In fact, it's like I did this before and the video malfunctioned, and so I had to do this again. Not that I'm bitter about that at all. Okay, 14e to the... Okay, so this function is exactly what I had here. And so you can also write this, depending on how many sig figs you have, as 60. Alright, where'd my last sheet of examples go? Here we go. Kind of like this folding thing. Gives me a little more room to work with here. Alright, so we got this function, which, sorry, this looks like my handwriting went a little haywire here. This should say 3/2 sine of g. The first two terms are just power rule approach. The last one is a sine of g. It's all taken with respect to g, so this should be pretty easy to evaluate. Okay, so let's just go about it. First, we got stuff added or subtracted from each other. That means break it apart. In other words, distribute the integral. Okay, so now that we're done distributing the integral, we can take all the constants out. Oh yeah, one thing I also forgot to include in the problem statement here is that g is in radians. Because there's a big difference between 7 degrees and 7 radians. You can keep the parentheses around the g here or drop them if you want. It really does not matter. Somehow the darker green, I grabbed the dark green pen instead of the light green pen. Anyway. So, integral of g cubed, that's just g to the 4th over 4. Integral of g is g squared over 2. Integral of sine is negative cosine. Okay, so we're done integrating these three terms, but we have to remind ourselves to evaluate this at 3 and 7. Okay, this is going to get a little crazy, because 7 to the 4th power, that's a big number. Nevertheless, you got to do it, and you know what, we got calculators to handle this, so it's not too crazy. But the 4's cancel out, the 2's cancel out, you can do a little bit of algebra to clean this thing up before you actually substitute. Okay, well, now there's no more avoiding it. We got to substitute in the big ugly numbers. Okay, that's what we get when we substitute in the 7. Now we got to substitute in the 3. Alright, we could do this by hand, but you know what, we got a calculator, so let's just use it. Okay, so we got 7 raised to, let's back up and put some parentheses here, 7 raised to the 4th power, minus 7 squared, minus 3 divided by 2 times the cosine of 7, minus 3 to the 4th, minus 3 squared, minus 3 halves, times the cosine of, oops, I forgot the multiplication symbol there, cosine of 3. Now, whenever you're using trig functions, always check to make sure your calculator's in degrees, in radians, or whatever the right units are. Alright, double check here, 7 to the 4th minus 7 squared minus 3 halves times a cosine of 7 minus a quantity 3 to the 4th minus 3 squared minus 3 halves cosine 3. Alright, this looks good. We've got 2077. Okay, that's a big area. But hey, you know, this is a third order polynomial plus a little bit of an oscillation, so you should get a big number. Last sample problem. This is either deceptively complicated or deceptively simple, depending on how you approach it. First thing to realize is that we don't have you don't know enough calculus to solve this function as it is. You know how to take the integral of sine of u du, but you don't know how to take the integral of sine squared of u du. Do not try to use the chain rule on this. Remember, chain rule is just for derivatives. So there has to be some trick to it, and the trick is, if you remember back from your trig identities, that sine squared theta plus cosine squared theta always equals 1. So if this works for thetas, it works for u's. So really, what this is just the definite integral from 0.5 to 0.7 of 1 du. Now this gets a lot easier. 1 is u to the 0 power. Sorry about that little spot there. That's just bleed through from the previous page. It's a disadvantage of folding things over. Okay, integral of u to the 0 is u, so this is u evaluated at 0.5 and 0.7, and so this is 0.7 minus 0.5, and that's going to be 0.2. Alright, so once you realize the algebra trick, then the calculus is easy. The other question you might have is, why is this so simple? Well, if you look at what this is, integral of 1 from 0.5 to 0.7, just graph that out. If we have u on this axis, u as in the letter u, not u as in you and me, and we have f of u on this axis, and this is 1. So what we've effectively done is we've said, okay, 0.5 is right there, 0.7 is right there, and what we want is the area under the curve and between 0.5 and 0.7. In other words, we want this orange area here. Well, this is really easy. This is just a rectangle. It's 0.2 wide, and it's 1 unit high. So if area is equal to base times height, and then our area is just going to be 1 times 0.2, and so your area is therefore going to be 0.2. You could approach, once you get this far, you can approach this problem either way. Alright, that's it for this video. Hope it was helpful.